Okay, gonna go over 4, 5, and 6 here for you. A disk initially rotates at 2 radians per second and comes to a stop in 3 seconds. Determine the angular acceleration of the object and the angular displacement of the object over the 3 seconds. All right, so the thing to keep in mind here is, when you are first starting these kinematic problems with motion, with rotational motion, omega is velocity, so omega naught, average. Acceleration is alpha. Displacement is theta or delta theta, and time is still just regular time. I know for some people it's helpful to just write the equations with x, v, and a first, and then copy the variables over in terms of rotational variables, right? So sometimes it's also helpful just to leave off angular or rotational. Just call this velocity, initial velocity, average velocity, acceleration, displacement, and time. All right? So when you're thinking about them, you got to think about them like that. Now, we can assume, since we're not given any functions or anything in these first two, that this is constant acceleration. And when it's constant acceleration, we can use all the regular old equations of motion. So the very first one we might have is displacement equals average velocity times time. Average velocity equals the average literally of the initial and final velocity. You can have L grande, delta theta equals 1/2 alpha t squared plus omega naught t. We could have the v squared equation, or the timeless equation, omega squared equals omega naught squared plus 2 alpha delta theta. Acceleration is defined as the change in theta, or change in velocity over time, and so on, all right? So constant acceleration, we can do that. So let's figure out what we got here. So the initial velocity is 2.0 radians per second. It's going to come to a stop. So final is 0. Look at that. I just wrote meters. 0 radians per second. All right. The time is 3.0 seconds. Okay. We're looking for the displacement and acceleration. So we know the average velocity is 1.0 radians per second. Angular acceleration, so let's, I guess, go ahead and do that first. Alpha equals change of velocity over time. So it's going down by 2.0 radians per second in 3.0 seconds. So that's about 0.67, negative 0.67 radians per second squared. All right, then displacement, delta theta equals, I just assume do average velocity times time. That's always easier. You could do L grande, but this is almost always the better way to go. Delta theta, 1.0, only if you know the initial and final velocity, though. I should make note of that. 3.0 radians. Now, so that's the displacement as it stops. So it's a pretty, it's not moving very slow, right? So let's try to visualize that rotation, right? So one cycle, one time around, is 2 pi radians, which is about 6.3 radians. So it's going 1, 2, 3, 4. So 1 rotation per second, or, let's say 1 rotation per second, 6.3 radians per second. So 2 radians per second would be about a third of that. So it'd be pretty slow. 2 radians per second is probably something kind of like that. So it's good to try to visualize this stuff in your head, especially when you're first getting started, Try to picture what's going on rotationally. Now, I should make note here, negative and positive with rotation. Counterclockwise is positive rotation. Clockwise is negative rotation, just like a unit circle, right? A positive angle is when we rotate counterclockwise. So, number 5, a disk initially at rest is subject to an angular acceleration of 1.6 radians per second squared. Determine the angular velocity of the disk after it has rotated over an angular displacement of 64 radians. All right. So I'm going to make my little table here. make it a little bigger this time so I leave myself some more room. Omega. This ink is flowing and I'm smudging it. All right. Initially at rest, so omega naught is 0 radians per second. Omega, I don't know. I shouldn't have written that there. All right, acceleration 1.6 radians per second squared, 64 radians. So it's about 10 rotation. 10 rotations or so. If it's 6.3 radians per rotation, it's about 10 cycles, 10 turns. I can't visualize that acceleration. I think it's kind of slow, but I don't know. We'll see. We want to find omega final. So omega final equals, what would be the best way to do this? We don't know time, right? Timeless equation. Omega squared equals omega naught squared plus 2 alpha delta theta. I love saying that. 2 alpha delta theta. So omega naught, 0. Omega equals the square root of 2 times 1.6 times 64. I just did this on the board with the kids, but in school, my calculator's been a little bit funny ever since I sanitized it. I guess I shouldn't have been quite so liberal in the application of cleaner. Yeah, 14 radians per second. So hard to not. So omega is 14 radians per second. Ignore that. That's straight mark, and I don't have any white out. Sorry about that. All right, so determine how much time it will take for the disk to achieve the 64 radian displacement. Well, I know the average velocity now is 7 radians per second. All right, I know delta theta equals average velocity times time, or time would have to be delta theta over average velocity. So 64 radians divided by 7 radians per second ends up being about, I think about 9.1. 64 divided by 7 is 9.1 seconds to get up to speed, or to get down to speed, or no, up to speed. So it's fairly slow. I was right. That angular acceleration of 1.6 radians per second is fairly slow. 9 seconds to get up to 14 radians per second. Now 14 radians per second, that's about 2 rotations per second. So that's moving pretty fast. Anyway, all right, so now on to the calculus here. So just like I did on the top here with the equations, you can do that for the calculus as well, right? So omega is d theta dt, alpha is d omega dt. I could also say delta theta equals integral of omega with respect to time, and delta velocity is the integral of alpha with respect to time. 0 to t, 0 to t, or t1 to t2, depending on how you want to think about the limits there. Yeah, so determine the angular acceleration at 1.5 seconds of rotation. So alpha is going to be the derivative of the velocity with respect to time. Acceleration is derivative of velocity with respect to time. So the derivative of this function is, you bring the 2 downstairs, so negative 2 times 4 times t plus 0. All right, so then to find it at 1.5 seconds, you got to put in 1.5 seconds for t. So alpha at 1.5 seconds equals negative 8 times 1.5, which equals negative 12 radians per second squared. All right. Again, negative just means it's accelerating clockwise. There's something rotating. Maybe this is something attached to a pulley or something is rotating it clockwise. Angular displacement of the object after 5 seconds of rotation. All right. Delta theta equals the integral from 0 to 5 seconds of negative 4t squared plus 6 with respect to time. All right, cool. So, antiderivative of that first, negative 4t cubed over 3 plus 6t evaluated from 0 to 5 seconds. So the antiderivative becomes the integral when we evaluate it over the time interval. So negative 4 times 5 cubed over 3 plus 6 times 5. All right? That's what you get when you sub in 5. If you sub in 0, you get 0. So subtract off 0 if you want over there. But anyhow, let's see here. 5 cubed is 125. 4 times 5 is 500. So negative 500 over 3 plus 30. That gives me about, let's see, negative 500 over 3 is like 167 or something. Or 1 over 3 plus 30. Gives me 140 to 2 sig figs. So delta theta from 0 to 5 seconds is negative 140 radians. All right, so quite a few cycles. About 20 rotations, I suppose. All right, and there you go. I'll scan this. I'll add this to my solutions for worksheet 3 and re-upload them, and then you'll have the full solutions. All right, on to this. I'll make another video really quick.